Welcome to the next lecture of Software Design and Modelling. Today we're going to talk about contracts and about design by contract, and then we're going to go on and talk about several different ways of approaching what I've called interaction design. These are pieces of design principles that focus on the dynamic behaviour of the system and how you can make it controllable, make it have the good design properties that we want. Starting with contracts then. In ordinary life, a contract lays out an agreement, often a legal agreement, between some parties, and it says what each party's obligations are and what each party's rights are. And there are fundamentally two reasons for having a contract. You want, on an optimistic view, to avoid misunderstanding. If everybody understands what their obligations are and these are explicit, then we increase the chance that there will be no misunderstanding and that these will be met. And on the pessimistic perspective, we also want to be able to assign blame. If some obligation is not met, then the terms of the contract ought to make it clear who is at fault. Sometimes it might lay out penalty clauses and the like. That you will not so often meet in technical software contracts, although you of course might in legal software contracts that relate to the development of the software. That's another matter. We're not talking about that kind of contract today. We're talking about contracts used as a technical mechanism to control the design of software. So the term design by contract was introduced, and indeed trademarked, by Bertrand Meyer, whose name has come up previously. And the idea here is that you use contracts as an essential part of the design of your software, and you systematically make explicit the contract between the supplier of each software service and its client. And so in this way, as we shall see, design by contract contributes to avoiding misunderstandings and hard-to-track bugs that might result from them. It supports the clear documentation of a module, so the idea here is that a client of a piece of software should be able to read the contract that the software is willing to enter into, instead of feeling the need to read the code. It supports defensive programming, which is to say, sometimes you want to program in such a way that you allow for the possibility that the other party doesn't meet their contract, but something that occurs in a pair with that is that it allows the avoidance of double testing. You can avoid putting in tests that might otherwise be necessary if you wanted to check good behaviour of a party, but it hadn't been made explicit whether or not that party was agreeing to always provide that good behaviour. We'll come back to that later on. Software contracts may be supported by tools and automatically checked, dynamically or occasionally to some extent even statically, or they may be purely for human reading. But the key thing is that design by contract says that there should be explicit contracts attached to the responsibilities that a class exists to fulfill. And there are basically three kinds of contracts that occur. There's this pair that applies to a method. A method has a precondition and a postcondition. And the precondition lays out the things that the writer of the method is entitled to assume will be true when the method is invoked. So we've said here that if the precondition fails, all bets are off. Okay, you can't blame the writer of a method for how that method behaves if the method's precondition was violated. Okay? The postcondition is what the writer of the method has to ensure. So the method promises to ensure that the postcondition holds, provided, of course, that its precondition was met. So the precondition are the rights, the things that the method writer can assume, and the postcondition are the obligations, the things that the method writer is obliged to ensure. And also a class has an invariant which it has to maintain whatever happens to it. So whenever it receives messages and responds to its messages, it needs to maintain its invariant. You can think about the invariant as being a statement that has to be true of any object of the class for that object to count as valid, as being in a sensible state, in some sense. And there are some slightly interesting questions about precisely when a class invariant has to hold of a given object. For example, supposing you say there must always be exactly one object linked to it of this kind. It might be that there's some stage during internal computation after you've removed an old object and before you've added a new object in which there are 0 objects linked to it, and that's usually okay, provided the outside world can't interact with an object while it's in a bad state. Okay? But the invariant lays out what it is for an object to be in a good state, in a valid state. Okay. In the context of object orientation, a particularly interesting thing to worry about when you think about how contracts work for methods is, well, what about when a subclass re-implements an operation, overrides an operation? It has to fulfill the contract that was entered into by its base class. Otherwise, we can't have any reasonable kind of substitutivity, because a client, which is written in terms of a base class, has to still work when it is handed instead an object of a subclass. And because a client will be assuming that any object it's being passed is obeying the contract that was made explicit and laid out for the base class, that implies that every subclass must also obey that same contract. Okay? Now, it might be that the subclass provides an even better contract. What does better mean in this context? Well, it's laid out by this rule of subcontracting: demand no more, promise no less. If you think about it, this is what you want of a subcontractor in everyday life as well. Okay? It's perfectly fine for a subclass to weaken the precondition, in other words, to work correctly in more situations, but it's not okay for a subclass to strengthen the precondition, in other words, to demand more, to work correctly in fewer situations. Okay? And on the contrary, it's fine for a subclass to strengthen the postcondition, in other words, to promise more stringent conditions will hold, but it's not okay for it to weaken it. So, for example, if you have a method that takes an integer and returns an integer, and we say in the base class this method only works on positive integers, but it makes no promises about what kind of integer it will return, then we're perfectly happy if that method is overridden in a subclass by a new version which no longer insists that its input integer should be positive, but instead works on all integers as input. And where the base class made no promises about what kind of integer would be returned, we're also perfectly happy if the subclass promises that the integer that it returns will be positive. As far as clients are concerned, the subclass is obeying the contract that they expected to be entering into, and that's fine. Now, remember that the Liskov substitution principle, which we saw earlier, was an attempt to say when subclassing was safe without having explicit contracts. And so you may wonder, well, what are the pros and cons of these two approaches to saying when subclassing is okay? Effectively, in order to obey the Liskov substitution principle, what it amounts to is saying that a subclass has to obey whatever contract for the superclass is in the client's mind. So any contract for the superclass that could have been written down and which the superclass would have obeyed must also be obeyed by the subclass if it is to be obeying the Liskov substitution principle. Okay? And that, in fact, is why the LSP is actually too strong to expect it to hold in all good designs, because some of the contracts that the base class could have been obeying are not actually things that the writer of the base class ever really intended it to be obeying. Okay, they could include things which just happen to be properties of the implementation. Then the LSP insists that those are maintained in all subclasses, but that isn't usually really what you want. It constrains the writers of subclasses too much. On the other hand, it really is about the best you can do if you're not willing to make contracts explicit. Okay? So if you do something like design by contract and you make contracts explicit, then you get the benefit that you can have extra flexibility by means of laying out exactly what properties of a class clients are allowed to rely on and what they're not allowed to rely on, because clients must not assume any more than that the class will obey its contract. That's the purpose of the contract. Okay. Now, we've seen a little bit in passing before about constraints in a UML model, so I'll go through this quite fast, in fact. In particular, you read about OCL much earlier in the course, so I will definitely skim over that at this point. But constraints allow you to give more information about what will be considered a correct implementation of a system described in UML than you can do using the diagrams alone. So a constraint will constrain one or more model elements, and this just means to give conditions which they have to satisfy. Okay? So they can be written in an appropriate language, and we'll see in a moment what that might be, but of course OCL is the classic example. And as you've seen, they're enclosed in set brackets, curly brackets like that, and they're attached to the model in some visually clear way. So for example, you may put them in a note and attach the note via a dashed line to the relevant parts of the diagram. So let's look in a bit more detail at the kinds of contracts that we have that are relevant in object-oriented designs. So a class invariant restricts the, I've said here, the legal objects, the valid objects, by specifying some kind of relationship between the attributes of the class, perhaps, and or the attributes of associated classes. So you might, for example, have a class which has an attribute name of type string, and you might give a class invariant the name is no longer than 32 characters. Okay. Implementers of that class have to ensure that the invariant is satisfied, and as I said a moment ago, there's a slight question about precisely when it has to be satisfied. It may be too stringent to say at absolutely every instant. Clients of the class may assume that the class invariant will hold, and of course that is the major clue as to when implementers of the class have to ensure that the invariant is satisfied. It must be satisfied whenever a client of the class might start interacting with it. With an object of it, we should be saying, of course. Okay. We can also write class invariants that constrain the configuration of objects in the system. And the example we have here is that suppose we have a class student which is associated with two different classes. One of them is director of studies and one of them is lecturer. And you should imagine that every director of studies is a lecturer. Okay, so it is possible in principle for an object that is linked to a given student, but considered as director of studies, might turn out to be the same object as the object which is linked with the student when the object is considered as a lecturer. And suppose that's not allowed. Okay, the student's supposed to have two different people that they can go to. And you can represent that by a class invariant on student. We could write in English, student's tutor and DOS are different. And as always with constraints or statements about software expressed in English, we have to ask ourselves, is that sufficiently unambiguous? Now that's a question for you to take away and ponder. We can constrain the behaviour of operations using pre- and post-conditions, and as I said, a precondition has to be true before an operation is invoked, and a post-condition has to be true after the operation has been carried out. So here's a simple example, which reminds you, I hope, of the syntax for expressing pre- and post-conditions, if you haven't seen it before. Or rather, it reminds you of it if you have seen it before, and it tells you if you haven't. I forget whether you have already in this course. Anyway, okay, so we've got an operation register of a class module, let's say, and register takes an object which we'll call S of class student. And the precondition is supposed to be that the student is not already registered for the module, and the postcondition is that the set of students registered for the module is whatever it was before plus student S. And notice that in addition to the usual questions about whether the English is sufficiently unambiguous, we've also got strategic or design questions about exactly what we choose to write down in the contract. Now, I said in passing a moment ago that clients should not assume any more than is specified in the contract of an operation. And that certainly lends itself to a quiet life. That's good. Sometimes you might want to have contracts that don't lay out absolutely everything you want people to assume. So you'll quite often see that people might write postconditions that might just say some of the things that should be true. So you might, for example, see as a postcondition, S is registered for the module. Okay. Now the key difference between that and what we've got here is that if we just said S is registered for the module, then the register operation which threw away all students who are currently registered for the module and returned you a situation in which only S was registered for the module would then meet the contract, okay? Which is probably not what you want, so that's why we've got a contract here which is expressing something a bit more stringent. It's saying it's whatever it was before plus student S, okay? And exactly what you say is quite likely to depend on the language in which you're saying it. It turns out, as you may remember, that OCL has a decent way to say the version of the English we've got here. Some other languages you might use might not give you an easy way to say that, and this may influence what you actually choose to write down. So things are always a little bit more messy than they might be if you look at the ideal situation. So let's recap the purposes of contracts that we advertised at the beginning. So we claimed that the use of contracts would contribute to avoiding misunderstandings and hard to track bugs, and the reason is that the assumptions and promises are explicit, and so if you've got all contracts explicit and they dovetail nicely, so you successfully arrange that you can verify, at least manually, that preconditions should be satisfied in appropriate cases, then it should be fairly straightforward to work out which chunk of code it is that doesn't fulfill its contract, and then that's where the bug is. Contracts should support clear documentation of a module. In fact, reading the contract should be enough. They support defensive programming, so for example, when you implement an operation, you might wish to verify that your post condition holds before you return. Otherwise, instead of returning and leaving the software to fall over at some later point whenever it mattered that the post condition didn't hold, you fail gracefully at that point and report a bug. And on the other hand, you might avoid double testing by saying, when I'm implementing an operation, I don't need to check that my preconditions are satisfied because I'm assuming that the client will ensure that, as I'm entitled to do, because that's the role of the contract. Now here actually you might want to say, no, I'm going to do defensive programming here. I'm going to check that my precondition holds, and I'm going to fail gracefully, and I'm going to say there's a bug in whoever called me, in order essentially not to be blamed for a bug that wasn't your fault. And there's an interesting kind of trade-off between defensiveness, which makes it easier to track down bugs and may avoid the possibility of catastrophic failure, against the performance improvement that you may get by avoiding double testing. And which of those approaches is better will depend on the context in which you're developing. Writing contracts in English can, as usual, be ambiguous, it can be long-winded, and of course it can be hard to support with tools, although I have to say the natural language processing people are getting much better at this these days. You may have seen some very impressive work with testing based on writing tests in English. Nevertheless, careful English is very often the best language to use, because you can assume that you're working with people who are fluent in English, usually international development aside. And using English, or whatever natural language is appropriate in your setting, certainly beats using a formal language that the people who need to read it can't read. Okay? So, if English is not formal enough for your setting, you might consider using the chosen programming language. So for example, if you're developing in Java, you might just write a Boolean expression in Java that ought to evaluate to true. That has the advantage that you can paste it into the implementation, and you can maybe even check it at runtime, and also that if you're working with people who are expecting to implement in Java, it's probably safe to assume that the people who need to read the contract can read the contract expressed in Java, which is very valuable. But it may be too low level. Actually, lacking quantifier is not such an issue these days, but you may not find it ideally expressive. You may want to use plain mathematics and or logic, which can be helpfully simple. You don't need any special knowledge or facilities, but it can end up being the worst of all worlds, so it can be unfamiliar to the people who need to read it, and at the same time you can lack UML integration. You might want to use a dedicated formal specification language, and Z and VDM are venerable ones, although then neither of them is so much used these days. These can be truly unambiguous, and there is some tool support for them. But they're unfamiliar to most people, and therefore not only people who have to read the contracts may find it difficult to do so, but also there's unfortunately a strong possibility that people who have to write the contracts will make mistakes. And if there's one thing worse than not having a contract, it's having a contract with a bug in it. There can be some non-ASCII considerations, and integration with UML is kind of a problem. You may need a special UML integrated dialect. Or you can use the object constraint language, which is obviously the intention of this language, and you've met OCL. I'm not going to say a lot more about it so far. Some people like OCL more than other people do, but it's an obvious language to consider for contracts when you're working in UML, or indeed any related language, for example, any domain-specific language that's based on MOF. So it was aiming for the sweet spot between formal specification languages and the use of English, trying to be formal but easy to learn and use. There's some controversy about whether it's really achieved that. It used to be extensively used in the documentation of the UML language itself, but not quite so much these days, which is quite telling in itself. There was a lovely paper in Models a few years ago that went through a version of the UML standard and analysed the OCL that was used in the standards document itself, and found a scary number of bugs in the OCL constraints that were in the UML standard, which is a bit sad. It's written in plain text with no funny symbols. Used to have some serious semantic problems, but I think it's fair to say that those are basically solved now. There is some tool support, and I'm not really going to advocate that you go out and do design by contract, writing contracts in OCL for all your object-oriented systems, because I think contexts in which that's a sensible idea are few and far between, but it is worth knowing a bit about.